FALL18Thermoelectric project, and our team name is WATCH, which is an acronym for Wear a Thermoelectric Calorie Harvester. I'm Justin.
I'm Jace. And I'm Alex.
So here's our project picture. These are the two most important components in our project, which is a heatsink and a TEG module, which is a thermoelectric module. The heatsink is important because it allows to create a temperature gradient across the module. So the thermoelectric principle operates on that. A temperature gradient is able to create electricity.
So just a little bit of background. Our society is very dependent on batteries. We use it in pretty much every part of our lives to power almost all of our circuitry. And it's actually pretty harmful in many ways. The electricity we use comes from not so clean sources. Batteries can be harmful to the environment by creating air pollution and also polluting the water that we drink. And it can be directly harmful to humans through lead, sulfuric acid, and other components that make up batteries. So we thought, what can we use that's reliable and can potentially power a lot of low power circuits, and we thought about body heat.
So just a little bit fun fact about how our body heat behave. Our rest radiates 350 kilojoules energy per hour, and that energy is equivalent to the energy given by 98 watts incandescent light bulbs. And with the surface area of human skin is around 27 meters square, from what we run from 130 divided by the energy over the certain area, we actually achieve the heat flux. And since we are focusing on our wrist with an effective area around 10 centimeters squares, multiply the heat flux over the area, effective area, we actually generate 57 milliwatt useful energy. And the picture on the right here was a prototype I did for a body heat powered mobile fan. It actually runs on a hot plate and also with hot steam gases. And after several modifications, we actually made it work with body heat for around 15 seconds. And basically how thermoelectric material in general works is it's governed by the figure of Marie. It's ET, characterized performance of TEG module. As you can see from this equation, we want to maximize the electrical conductivity while minimize the thermal conductivity. And the way how each thermoelectric couple works is combined of a p-type and n-type semiconductor, connected in series with all those copper interconnect, and eventually sandwiched by two insulators, which is commonly ceramic plates. And voltage generated by a thermoelectric couple is proportional to the difference in the Seebeck coefficient between the material and the temperature gradient between the hot side and cold side across the module.
So our goal for this project is to determine the feasibility of using latent body heat to power a circuit, or in this case a watch. So our objective was to design a watch that can be powered by a thermoelectric generator. This includes creating a low-power model schematic with optimized components to minimize power consumption. This utilizes a thermoelectric generator, a microcontroller, a display, a heatsink, and any necessary integrated sensors that can help us keep the power consumption low. It also includes parameterizing the application of our TEG such that we can reliably meet the power requirements. This includes designating the position of the TEG housing on the body, and also characterizing the performance of the TEG through experiments and software analysis, as well as analyzing the material properties for heatsinks and the TEG housing.
So as for requirements, in order for it to be considered what we would consider a useful wearable, is it would need at least a microcontroller and a display. So the microcontroller it uses an internal real-time clock calendar, and the display obviously displays the time. So we found that the power requirement at minimum would be around 3 megawatts, and our TEG module under our operating conditions would be able to produce about 0.36 volts for open circuit load or open circuit voltage, which is unusable. So we need a voltage booster, which would be able to boost our voltage up to usable levels. And a voltage booster works essentially by increasing voltage at the expense of your current. So as long as your power drawn is less than your input power minus your loss, then you could boost your voltage.
So here's a timeline of the important milestone and the documents that we instituted. But basically, it can separate into three parts by each quarter. The first quarter is primarily focused on the preliminary design and modeling, and also customization of material. And then by the beginning of the winter quarter, we will have the material ready, and we can run experimentals and prototype testing modifications. And then at spring quarter is where we manufacture the products and do more testing on the product, and eventually documents our project. And here's the resource and subsystem breakdowns. Basically, we will have like a faculty advisors guidance by Professor Jacob Lee, and along with his two fellow graduate students. We have any questions about lab space and equipment or circuitry and heat transfer, we can always increase his two graduate students. And also, we also have bi-weekly meeting with Professor Lee to update our progress. And basically, we are broken into 4 different subsystems, which call evaluation of potential wearable TG application, design integration, numerical simulations, and performance and reliability tests. And for the part of the performance and reliability test, we actually is a co-project with the undergraduate research project, the Europe. And the total number of units enrolled is 19 units, so which means the total hour for the first 7 weeks we complete is around 500 hours.
So just a little bit of progress on the potential TEG applications. We brainstormed with our team to find a suitable TEG application, which was the Wear a Thermoelectric Calorie Harvester, or WATCH for short. The wrist is an optimal location for the TEG because your arteries pass very close to the surface of your skin, and so that gives us a consistent and reliable heat source for the TEG power. We also researched some necessary components to assemble the watch, which is the microcontroller and the display. In the microcontroller, since we're looking for low power consumption, we don't want to use something that's going to create a lot of code and power consumption in that way. So we're looking for a microcontroller that has a real-time clock calendar embedded in it, as well as a charge pump, so that we can capture the low amount of current that we have and release it once we have enough to actually power our application. For the display, we also found that the electronic paper display, or EPD, is very efficient because it has static pages that don't consume power when they're not being updated, and there's no backlighting required. So here there's just a small table comparing an EPD module to a relatively sized TFT LCD, which is what phones typically have. And as you can see, for an entire day of 1,440 updates, the EPD would only consume 2.4 milliamp hours of power compared to 720 from the LCD.
And then for design and integration, this is basically kind of how we came up with our power output figures and the cold side temperature. So we used the specification sheets for the voltage booster to compare our open circuit voltage to our theoretical power output. And then from that, we were able to do SolidWorks calculations to figure out kind of what our cold side temperature could be expected under these conditions for ambient temperature. This is all under free convection mode. So. And then over on the left side, we have just our circuit schematic.
So in order to identify the design limits and the constraints for wearable TG applications, like using body heat, we actually run a lot. We actually put an emphasis on simulations. The pictures on the left were achieved by using ANSYS Thermoelectrics, and we actually performed the simulation in 2 different cases. One case, or the ideal case, which is like constant temperature on the 2 sides. The hot side is about 37 degrees Celsius, which is our body. The other side is the temperature of the ambient, which is 20 degrees Celsius. However, that's not how it behaves in real life, because in real life there's a lot of losses. And as I mentioned previously, there's a constant heat flux coming out of our body skin, and the other side is not always fixed to 20 degrees Celsius with the ambient, unless we have an effective heat sink that can cool it down. Otherwise, we have to consider like convective heat transfer. And between the two simulations, we actually see that the open cell voltage actually dropped by 1 volt, which is a significant amount if we are considering like constant heat flux rather than the ideal cases. And also with the simulation, we can verify the linearity, the relationship between like with increasing in from electrical pole, we actually can have a linear increase in voltage. And this is what a commercial TG unit looks like. And we simulate the whole module. We found out that the voltage generated by the TG is within an error of like 0.1% if you are comparing like with 199 couple conducting series, like 2 different ways of verifying it. And also to perform a parametric study of thermoelectric couples and to evaluate the change in electric potential with respect to geometric changes, we choose 2 control parameters, which is the height of the TG length and also the cross-sectional area. And these results were done on COMSOL's multi-physics. And as we can see some interesting relationships with an increasing in TG length, we actually have an increase in voltage by like 0.1 millivolts. That's only for 1 couple, but if we have like 199 couple connecting series, we can actually have like a 20 millivolt increase in voltage by just doubling the size of the leg. But unfortunately, we found that with increasing in cross-sectional area, we actually saw a decrease in electrical voltage. However, those relationships will guide us to like customize our electric module in terms of its geometry. And here for the performance and reliability test, and here's a simple figure of like how our experimental circuit runs to like measure the conductivity, figure of variator resistance. And with the knowledge we run from 120, we actually can identify the temperature across different layers and eventually compare with the result we obtain from the IR camera.
And then this is a quick breakdown of our budget. The price variance could be due to whether or not we go with an off-the-shelf component or a custom-made component. So our total expected cost should be between $450 and $600, but with funding from Europe around $100.
Thank you.
Okay, thanks.